Hello everybody. Today we talk about the vector calculus, the basic why vector becomes so important in the math. Actually, it's demanded by physics, right? So the physics, you know Newton's equation, F equals ma, and a is acceleration, which is dv dt, right? But the v is the velocity, which is ds, the distance you go over dt. So F equals m d square s dt. That's what we learned in the physics. Now, here's a question. We live in a 3D world, right? And suppose you have a f expressed by vector f, and this m mass make a move, and this movement, the distance is s. This is a vector, right? Location of space is expressed by vector. So naturally you can think of Newton's equation in vector format. So what does this mean? This means S equals xi plus yj plus z k, and this derivative is simply dx dt plus dy dt plus dz dt, right? And this is what? Velocity. So vx plus vy plus vz. Now, here's a big assumption. In the Newton's physics, right? The vx, the vy, they don't interact each other. They are independent. Okay? The acceleration too. It's not like, okay, you are here and you move x direction this much, and that means y is the same and z is the same, right? And speed too. If you have speed vx here and you have vy and vz, the total speed is vector addition, right? This and this you add it. So vx, vy, vz is independent variable. Okay. You may say, well, wait a minute. You have this kind of case. This is mg you did in the physics, and you what do you do with this kind of things? You divide into two vectors, and when it's orthogonal, then they don't interact each other, right? If vector is not orthogonal, this has this component and this component. So if you break it into orthogonal, then it doesn't interact each other. And why? Is there anything special about 3D world that orthogonal is very important? It's treated like exception? Well, this is a big assumption in the Newton's. The space is like this, unless you go to Einstein world. Then story changed. But in the physics, in the high school, you are dealing with Newton, so it's a big assumption is orthogonality has a meaning. Whatever is orthogonal, they go independent. Okay? Because 3D is defined by this orthogonal. Well, actually, mathematically, you can play with this. You can make not orthogonal coordinate and break into this non-orthogonal coordinate, right? But then vectors addition is going to be a little bit more complicated. Okay, so basically this is a vector. So Newton's equation, you can use vector. That's great. Okay, and is this the vector calculus? No, hell no. This is just the entry point. You get the taste of vector calculus. Okay, so then why make a big deal out of the vector calculus? Okay, the first problem, physics problem, demanded, for example, say you have this kind of tube and water is flowing, right, and making a curve. So how do you analyze this kind of fluid, right? It's called the fluid dynamic. This is the college physics. So to analyze, okay, only things we know is Newton. So Newton, you have to look at mass here, and the mass here, and the mass here. These mass move along the curve at v and acceleration, right? And there you divide this into many small mass and put the summation and make an equation. This is really complicated, don't you think? So naturally they couldn't make any progress. How do you deal with this fluid physics things? And here's the genius guy is Lagrange, right? He said, well, let's assume it's flowing steadily. It's called steady state. That means you take any point, velocity is not changing, it's just flowing. Okay, so what we want to know is not individual mass of water moving on the curve. This is complicated. What we want to know is you take any point in this, the flowing media, you take any point, what you want to know is the velocity at that point. Okay, if we can get this one, we can pretty much analyze everything. Okay, so if it's not steady state, it's going to be x, y, z, and its function changed by time. And we worry about this later. It's complicated. This is a parameter we want to work with, not f equals ma. You make a vector if you like. This is not. This is what we want to know. Then there are a lot of results came out of this. But in order to have a result, we have to be able to differentiate this vector field. And this differentiating vector v by x or y or z, this one is differentiating with respect to t, time only, in the Newton. But suddenly you start having a differentiation by x, y, z on the vector field. And it's called field theory. And this field theory is expanded to electromagnetics theory, which it's a college physics. You get a bunch of differentiation by x, y, z, and when you include the t, you get the electromagnetic waveforms, and also even quantum mechanics. Because quantum mechanics, the particles appear to be distributed in the physical location. It's not in a single location. It's not particle. Actually, it looks like a wave, behave like a wave, but when you observe, it's observed like a particle. It's getting very complicated, the quantum mechanics. But that's also the vector field theory becomes the basic for this. So we talk about then how do you differentiate the vector field. Okay, before vector field differentiation, you have to know that you are now dealing with multivariable. Let's say this is S. Let's review a little bit. How do you differentiate the multivariable? ds is going to be dx dx plus df dy plus df dz. Do you remember? So what's the meaning of this? Okay, let's deal with two-dimensional case, right? Then you have S is kind of curved plane, and you have x and y, and f, x and y, the curved plane, you have a dot here, and you define plane touching this dot, and on this plane you define x direction and y direction, right? That's the dx and dy, and you can calculate how much ds change by multiplying this coefficient. So this partial derivative is a coefficient for dx and dy, and total change is dx, but that's on the linear plane, right? But what is the slope on this curved plane? Exactly same as the slope of this linear plane. It's the same idea as, say, you have this derivative, and this m is dy dx, dy equals m dx, and on this curve, if you take any dx, you can get dy by multiply by slope m, right? It's the same idea. So if you make it three-dimensional is, you cannot draw like this. You have to draw like, say, you have a density distribution, right? It's very dense around here and becomes sparse here. So x, y, z, and density is going to be the function of x, y, z. Or if it's symmetric, it can be r, right? Distance, density change only by distance from this point. Okay, So it's very hard to depict the situation for the 3D, so we use 2D, this example, to get the idea what this means. Okay, so this is the multi-variable differentiation. Okay, now then when vector function come in, what's happened? First of all, vector function, we define two different kind of multiplication, right? Inner and outer, right? It denoted by x, and this is dot. It's like A, B, and A multiplied by B. There's two different multiplication. So you can guess it's somewhat different from just a multivariable case. And beside that, there is a outer differentiation. What you get? You differentiate the vector function, you get the vector as a result. Well, that's only one case. Now you differentiate scalar case. Scalar produce vector after differentiation, and the vector to scalar and vector to vector. So we deal with three different kind of derivative function. Okay, now say density x, y, z function let's use potential. Do you remember the potential function? The Earth is here, and the potential energy is like this, because gravity is F equal G R square, and here's M, and G include Earth's weight and gravity constant together. So basically function is like that, and this is the vector. The gravity works this way, but if you calculate the potential energy, phi is right, the constant we just put it G prime, so M over R. So this is a potential energy. What is the potential energy? Potential energy is like say this is the sun and Earth is here, right, and Mars is here. There is a potential energy difference. So in order to go to Mars, you need this much energy to move the satellite mass over there. Okay, now Jupiter is outer space, Saturn is even further, and comet usually go around from their Saturn or Jupiter, that area, and come all the way to the sun. So potential energy is converted to kinetic energy. The speed keep increasing and become super fast, and go around the sun and go back there, and they repeat like a 500 years per cycle. When it's come around Earth, it's like 200 Mach 200 means 200 times faster than sounds, right? It's so fast. Okay, to send a satellite to Jupiter or Saturn, you need to shoot the satellite by this kind of kinetic energy Mach 200. Otherwise, Sun gradually pull it back. Before it's reached to Jupiter, it's come back. Okay, in order to go all the way, to go around like a comet, right? The comet, this much energy, kinetic energy around the Earth. Then kinetic energy is used for potential energy to go getting close to zero potential energy. If you jump out of the solar system, then you can keep flying because no more influence of the sun's gravity. But around the Saturn and Jupiter, influence of gravity is still very strong. That's why they can keep going around Sun, right? Yeah. So somebody said, oh, we can send a satellite to the Saturn. How can you do that? We don't have a technology to, accelerate 200 Mach 200. Right now, so going to the moon, we use Mach 20, and that's the technology we have. 200 is too much energy. How do you generate that much energy to shoot satellite going to the Saturn? Impossible. Right now, we don't have such a technology. But some people thinks, yeah, we are Star Trek. I mean, we can do anything. It's just physically, you do the calculation. There's no way you can do it. Okay. Now that's a sideline. So this potential energy here, force is vector actually. This is R. We write it this way: R over R. R is the size of R vector, right? So this is unit vector, whatever the direction. If you choose I as a direction, so we can write vector F equals G M R square R vector over R. This is just a unit vector, direction only, and this is the amplitude of the vector. Okay, now you see the relationship between potential energy, and potential energy is a scalar, right? And the force is vector. And how do you do this? This one, if you remember, you integrate to get potential energy, because you have a force. The way you calculate is you have a force acting and you move this much. This is gravity direction. Then you integrate, you calculate how much height you gain. That's a potential energy. So you integrate to get this potential energy. So say if we have a potential energy function, it's going to be the derivative of force function, and this one inverted triangle is a delta. It's actually, there is another delta, so we don't call delta. Some people call nabla. Okay, so nabla force. This means you have force, and this is wrong. I'm sorry. This is opposite. This is integrate. So you have to integrate potential energy to get vector force. Sorry about that. Okay. So this is a vector. It should have a I, J, K, right? So what we do is we define this as operand, mathematical operand. Okay. Well, you can use cylindrical coordinate. It's other the coordinate is possible, but x, y, z, they become like this operand. So potential energy is going to be I plus partial derivative, and this becomes j component and that is the F force. Okay, so this partial derivative is a coefficient of I vector and j vector and k vector, and nabla phi it's called gradient operator. So gradient operator work on scalar like a potential energy. So gradient is taking a slope of this, and when slope is higher, then pulling by sun, the force is stronger, and the force become less and less, but still has influence, enough influence to move such a big planet like Jupiter going around the sun. Okay, so the solar system is completely dominated by sun's gravity. Its sun is that much strong and great. Sun control everything within solar system, and only Star Trek can keep flying without any energy. Okay, forever. Even sun is there pulling you. Ignore the sun and just keep flying it. Okay, that's Star Trek. So it's a fiction. Okay, so this is a case. Scalar become vector, right? So if you have a vector, after derivative becomes scalar. Okay, so I don't want to get into electromagnetic field the physics too much, but say it's good. Suppose you have a sink and the water is draining, right? And you surround this, and you have a here amount of water flowing. Say this is a D vector because it's depend on location, right? Okay, so you can have a derivative of D, right? So this is different. This is a scalar. This is an inner multiplication. So D is amount of water flowing, dx I plus dy j plus dz. This d is not good. Let's make it amount a. A equals ax I plus ay z plus az k, right? I j k. and the vector shows how much, which direction water is flowing, and that derivative becomes some unique constant of this sink. You have a sink size, how much you can drain, that is going to be related to derivatives of, because this is a rate, d is the amount flowing, right? The rate of amount flowing is going to be related to the size of this sink, right? So this is a nabla, how it works. Since nabla is this, and d is this, we change to a, d is confusing. So it's going to be ax plus ay az, because this I and I times I, inner product is 1, scalar 1, and I times j, inner product is 0. This orthogonal vector is all 0, only same vectors remaining, so it's become like this. Okay, and this nabla is called divergent. Divergent A. Are you having too much today? Well, let's listen to it as you learn this anyway, mostly in the physics in the college. Now, last one is, how about outer product? Outer product operator is defined not by this, but something like this. And matrix and ax, ay, az. So for example, I direction will have this much az minus ay az plus j, same way. If you break it down, this determinant into the equation, it's become like this. This looks complicated, but this is exactly what physics need, because you have magnetic field, right? And you have an electron coming in. It's generate a force, and the force is this electron's vector and magnetic field. It's like this, right? Orthogonal to two vectors, right? Okay. So derivative of magnetic field. Okay, this is another vector force. So in order to calculate the force, we need to do multiplication, but the outer product. Okay, so physics, we use this, using those derivative. You know, if you have a derivative, you can have a differential equation, right? For example, this kind of differential equation. You you take a derivative twice, it's come back to the same function, so obviously probably it's a sine function, right? But it's become negative if y equals sine. You take a derivative twice, and this is sine. Sine, say omega t, so it's omega t omega twice, so m equals minus omega. Then this differential equation can be solved. Answer is sine omega t if m equals negative omega t omega square. Okay, this kind of solution exists, right? So you take a differential equation, so you have 4 different differential equation using vector derivatives, and that gonna be the basic of electromagnetic field theory, equivalent to Newton. Okay, so we don't want to get into too much physics here, but that's the reason why vector calculus become very important, because it's become the foundation of one of physics field: fluid dynamics, electromagnetic field, and it's evolving to quantum mechanics. Okay, I hope you enjoyed today's video, and please subscribe if you like, and wait for the next subject.